Okay, so next week we'll have lab 2, just to remind you. So Monday and Tuesday groups. And so lab 2, if you had a chance to look on the D2L site, so I have the lab outlined here. This kind of builds on lab 1 in some respects, because last time you just made the planar grading. Now we're going to use a spherical wavefront to record in conjunction with a planar wave. So here's the geometry. So we have some lens here that has some focal length, like so. And then we allow that beam to expand out. We have, of course, there's going to be a curved wavefront like that. And so this is actually going to cause some problems for the exposure, because you're not going to be able to get a uniform or a common exposure across the aperture, right? Because here we have, if this is the radius, so we have the highest beam irradiance that's going to hit that film plane is going to be along the axis. But then as we go off the axis, we're going to lose the intensity by 1 over r squared, right? So that's our common intensity or irradiance relationship. So out at the edges, you're going to have kind of a different exposure density out there when you do this. So you'll have to kind of compensate for that a little bit. I'm not really asking you to do that. I'm just asking you to, in this lab, what you'll do is kind of explore some of these issues, see how much of a problem it is, and how much of a change in efficiency and so forth that you're going to end up with for making this holographic lens. So let's just kind of go through this a little bit. I don't know if Silvana has a pre-lab. I'm not a big fan of all that. I just kind of like to have you address some of the main issues here. So I have a procedure and then a set of questions. So the bulk of the lab is going to be, kind of addressing some of these questions as far as your write-up goes. So here, all right, so we set it up for a transmission type lens, as I just showed you. And so measure the focal length of the lens supplied by the TA. Does everyone know how to measure a focal length? In two, yeah, hold it under the light. Like you have a light above and you hold it and then you see how far, your image forms of that light source. So in 2 seconds you can do that. It's a good qualifying exam question, somebody's going to ask you, or an interview question. Anyhow, that's, again, focal length, the light comes in parallel, focuses to a point. So this gives you, so I want you to look at that, kind of examine the lab setup, learn, it's a good experience to get a little bit of hands-on, learn the lab setup, measure the diameter that you have at the aperture. You don't want it too big, so you overfill, but you don't want it too small, because I want you to do some measurements within that aperture, all right? So, about maybe, I think for the lens, a diameter of about 1 inch is pretty good, something like that. So maybe, 2.5 centimeters or so is pretty good. And then, we'll have an off-axis reference wave, planar wave, try to keep it about 20 degrees. So you do it the same way that you did in lab 1. You do a retroreflection, and also you should do kind of a bit of a retroreflection for the focus beam. You can do that maybe prior to putting the lens in that beam path, right? So this lens may not be inserted. You have 2 plane waves coming in. So you can adjust the 2 plane waves first so that they have about a 20 degrees 20 degrees between them. And usually that's the way I like to do my setups. You know, I'll do everything, kind of rough it out without the focusing elements in the lineup of the optics. You know, keep everything very simple initially, and then that'll also help you to align, you know, the lens and so forth to make sure it's on axis once you have that planar wave going the way you want it. And so another thing is you kind of want to, it's best to keep the emulsion side towards the beam coming in. Why do you think that is? Yeah, and it will also allow you to kind of minimize any sort of aberration that you might have, kind of having that beam come through the glass. You may incorporate, you know, you're going to record the wavefront, whatever that is. So if you have a piece of glass there, you're going to record whatever in that glass. This way you have just the direct beams coming through. And it also allows you, as you mentioned, you can do your index matching much easier with the glass side on that back surface rather than the emulsion side. So, because then you would end up gooping up the polymer with index matching fluid. You can do it, right? But again, it would kind of make things a little less neat, I think. All right. So then, again, so we haven't gone through this yet, but to get maximum sort of index modulation, as you might guess here, you know, in order to get maximum index modulation, you would have a reference and object wave that is equal in magnitude. All right, that gives you the highest visibility. Visibility is, we call that I max and I min. So we have I max minus I min over I max plus I min. This gives you the highest contrast or visibility that you can get. And so if with a value of 1 for each beam, you can match that. Now, so you match it at the center of the hologram, okay? But notice, so once you kind of peel off here near the edge of the aperture, then that intensity for this focus beam is going to decrease to some degree. Depends on what the focal length of that lens is. If the focal length is pretty long and you have kind of a slow system, it's not going to vary that much. Okay, so you can probably get by without having too much of a drop-off in the index modulation. So again, this sensitivity to this difference here is very much a function of the material that you have. So if your material has kind of you know, if you have your index modulation kind of looking something very, you know, has a very high slope angle versus something that has more of a gradual slope, you're going to see much more sensitivity to that difference, okay? The polymer is probably somewhere in between. You know, it has reasonably high sensitivity, but I don't think it changes extremely fast. Some materials that change very fast are like photoresist. They have, and they're made that way because they want really sharp edges. So whenever light hits a particular area, you don't want this sort of, you know, kind of gradual change. You want a very steep sidewall if you're doing lithography and so forth. So photoresists are very much like this. You know, silver halide and polymer might, you know, lie somewhere in between there. So again, I want you to explore that a little bit in this lab.
Are these the pre-questions or just the questions of the lab? It's just the lab questions.
These are the only questions that you're going to have. Okay.
Very good.
Yeah, You know, I guess I'm not a big fan of the pre-question thing. You know, I mean, you guys are grown-ups. You know, I think Silvana likes to have that to force everyone to read it. So she also helps me out in my PV class, as some of you know. Some of you have taken that, I think. And there I have undergraduates and, sorry, we have an undergraduate actually taking this class and doing very well. But, you know, just, you know, some undergraduates are not as disciplined, and so that forces them to read the lab prior. I'm assuming that you'll read the lab prior, and I'm also going over it, so hopefully you'll have, you know, be ready to, you know, ready to roll when you get into the lab, because we don't have that much time, and I'd like you to spend it addressing some of these questions and, you know, playing with the experimental setup. So I think I better check with Silvana, make sure she doesn't have anything planned. I'll tell her that I told you guys that you're not going to have any pre-lab questions. So, okay, okay. And if she does, then I'll discount them or something. I don't know. I don't want to, you know, kind of demoralize her either, because she's very helpful. Okay, so here, all right. So we have this high visibility, and then what I'd like you to do is, again, build on your experience from Lab 1, so you kind of know what the exposure level. Does anybody remember what your exposure level was?
Yeah.
In terms of millijoules per centimeter squared?
7 milliseconds in there.
Because I found something kind of unusual. So I was working with that material a couple weeks before you guys did the lab, and it's rated at 633 at around 18 millijoules per centimeter squared. Okay, and when I was exposing it at that level, I found I was only getting about 20% diffraction efficiency, which is kind of low for that, very low actually for that material. So I kind of played around, and I made actually a few errors in my exposure, and one of my errors, you know, brought me down around 6 millijoules per centimeter squared, and I got a big increase in the diffraction efficiency. So I was wondering, you know, for that material, that material is a little bit old, but usually when the polymer gets old, the sensitivity goes down rather than up. For some reason, the material has higher sensitivity. So I'm wondering, did you get something like around 5 millijoules per centimeter squared?
I thought we got something low.
Yeah, it's pretty low.
You got around 18?
I know we were in the second group and we had even lower than the first group. And they were
Okay.
Supposedly, when me and Ed did it, we had the highest efficiency out of the groups, and we had it around 6.
You had it what?
Around 6.
Around 6? Okay.
Yeah.
What was your efficiency that you get?
I can't remember.
Okay.
I just remember. I think it was around 60.
60? Yeah, that's what I was getting
Yeah.
to. So, I mean, the material is kind of losing its, you know, responsivity a bit, but it should easily get, you know, like 50, 60, you know, I've gotten 90% diffraction efficiency when the material's fresh, you know. Oh, and so anyway, so build, you know, take whatever exposure level you had, because again, this is a transmission hologram. Reflection holograms, you're going to probably find that you need to expose it a little bit more to get the highest efficiency. And I'll explain that later when we talk about the coupled wave analysis. But so you'd start out maybe with 6 millijoules, and then you know, drop it by 10%. You know, do plus and minus 10% around that. And the reason for that is, you know, again, you have this expanding beam. Try to get that beam centered, you know, in the aperture. Make sure your beams overlap nicely. It's kind of it's a bit more important here, because you don't want this off-center too much. You know, it'll still work. You know, the experiment will not be, you know, ruined or anything, but it gives you a much better result this way, to try to center your axis of this expanding beam with the axis of the center of your reference beam. And by the way, you should also, what I would recommend and what I always do too, is to measure, use a small diameter pinhole or something, or you can stop down. I think we have a little cover for that detector. So, and use that as a probe in your measurements, all right? So you should measure the reference beam as well as this expanding beam to kind of get an idea of how much the intensity varies over that aperture. Because this beam that's going in here, it's kind of a Gaussian. Now, ideally, when we have that collimating lens out here, right, so there's a spatial filter and then this collimator, there's kind of a trade-off because you want to expand the beam to what you need, but you're losing power when you do that. So if you have a kind of a low sensitive material, you're going to have to wait a long time, which means you're going to have very stable conditions in the lab during that exposure. I have made exposures out to like 6 minutes in our lab, not in that room, but in the other room, the first room there where we have our big, our argon laser in there. But it does really require a lot of precautions in order to get something to work out there. So you can potentially, if you have this too short, this focal length of the collimating lens, what's going to happen is you're going to get a very pronounced Gaussian profile in that beam, and that's going to copy. Okay, so you're going to have exposures here going to be a lot significantly lower than here. And again, in some material where you have this high sort of transition or response to exposure, it could produce very dramatic changes in the diffraction efficiency over the aperture of your hologram. Okay, so again, try to pay attention to some of those things, and if you have time, relate that to the material response. Try to learn as much as you can from the experiment. So at any rate, I'd like you to, I think I asked you to do this somewhere here, or maybe I don't, but I think this would be a good thing to do is, you could just measure it at a couple of points at the edge, halfway, and at the center, and also measure it on the other side, because that could indicate that your beam is off axis, okay? And again, that could cause issues as well. So you always like to do that I always like to do that when I'm setting up my hologram systems. And the index matching, again, you should do your index matching on that back glass surface. And a couple of things came up. One of my new students was looking at making some holograms. And so what he found was that he was showing me the holograms, and they're supposed to be transmission holograms, but they had a very high reflectivity, and the color was very uniform over the aperture, all right? So whenever you see that, that's indicative of a reflection hologram. A transmission hologram, it'll have some color, but it'll only have color when you get it at the right angle, okay? Because then it's dispersing the light that's coming from your source. But a reflection hologram is actually made to be viewed in white light conditions to some degree. And you'll see a nice color, and that means that the reflection hologram is filtering out all the broad band wavelengths and giving you just a very narrow band of wavelengths that's reflecting back to you. And so that's very important if you're making a display hologram where you may want to use it in white light. There's a really nice display. Any of you been down to that Kartchner Caverns down there? I don't know if they still have it, but there was a nice hologram of the Kubla Khan, the big, crystal growth thing. So they have a white light source in the back, and so you can actually see this hologram in white light, or they might use an LED or something like that, but it's a broadband source. So whenever you see that, it'll look kind of, if you're recording it in red, it's going to look red, okay? If you're recording it in green and there's some expansion, it'll look red too. So there's, you can be deceived by the color, but to some degree it's reconstructing at that particular wavelength band. So if you see that, that means that you didn't do your index matching correctly, because what you're doing then is you're recording a reflection hologram. So here's your film, right? Here's the glass. And you're getting, so you have a wave that's coming in this way and then a wave that's coming out that way. And so you have these counter-propagating beams. And so that's setting up fringes that are parallel to the surface, like we talked about for the reflection hologram. And sometimes you'll get a clue as to what's happening, because what you'll end up with sometimes is you'll see a line through there, and part of this will be clear or dark, and part of it will be red, really bright, reflecting. So that means that your fluid that you use kind of evaporated maybe a little bit or sifted away from this part, and so you're getting the reflection hologram there, but here you're not getting that reflection. You had indexed, so this is index matched here, but not there. Okay. And another common problem is sometimes you'll see some really pronounced diffraction rings, just like we talked about, the Airy pattern in the that's nicely recorded in the hologram. You don't want that, okay? So what is that caused by? What do you think that's caused by?
Like particles?
It could be, but most likely, and 95% of the time, this is caused by putting an aperture here, for instance, which is pretty far away from the film, and it allows it to produce a nice diffraction pattern by the time it gets to that film plane. Or you can have one here as well. So you do want to define your aperture, right? You don't want to have it completely, expanded, especially if you're trying to get a couple of exposures onto the film. But try to position your aperture that you're using as close to the film as possible to minimize these diffraction rings. Otherwise, it's going to cause some problems during the recording. Okay. All right, just a few little tidbits, but those are useful things for making some good holograms. All right. So that was the procedure part, and then all right. So here I am asking you what variation in beam intensity across the surface of the hologram, and then again use kind of I think we have a small aperture that you can place over the surface of the detector, so you can slide it across the beam and get an idea of what that intensity variation is going to be. Okay, and then here again, so what is the range of inner beam angles? So as you can see here, you're going to get you have a large angle there, you have a small angle there. So here the fringes are going to be far apart, and here they're going to be close together. So I'm asking you actually to maybe do that calculation here, and to do it at a couple of points so you can get an idea what's happening. So you could do it at maybe halfway point, the axis, and at the edge of of your aperture. Okay. All right, and then what I'd like you to do is to measure the diffraction efficiency. And so in measuring the diffraction efficiency, we want to reconstruct this with the conjugate beam. All right. So here, so the film is again actually going to be here. So this is another reason why you want to do that. Although in actuality, if you did it with the glass side on this surface and reconstructed it this way, and then you reconstruct it with the emulsion here and the glass there, it's still going to be okay, because you're actually encoding the aberration that you've produced by having that focus beam go through the glass encoded into the hologram. So it will correct for that. So this is the idea of phase conjugation. You know, you can actually, so this is one example of that. So if this were, say, the glass, you know, if you send a focus beam through a slab of glass, you're going to get a focal shift, right, from your geometrical optics. It kind of, it adds this index in the beam, which again distorts the wavefront a bit, and it ends up giving you mostly spherical aberration if this is an axial beam here, and it produces the equivalent of a focal shift, that spherical aberration. All right, so, but the hologram will actually correct for that through the encoding process, because you've recorded that, you know, that focal shift or that spherical aberration in the hologram during the recording. So then when you reconstruct it with the phase conjugated beam, you can eliminate that aberration, because the wavefront's going to go back to reconstructing whatever was there prior to, you know, that aberration. So it's really kind of magical, but it works very well. And this technique is used for all sorts of things, correcting for atmospheric disturbances and other things like that. So there's a lot of really interesting applications for phase conjugation. Okay, again, so a simple experiment, but we can learn a lot from going through this. There's a lot of really interesting things hidden in this. So during the reconstruction, we're going to again put put a small aperture here. Try to keep it, you know, reasonably close to the hologram, and illuminate it at a couple of different locations, and measure the diffraction efficiency that you get, you know, with your beam probing this aperture of that hologram. And so what you might find, again, is it's kind of a reflection of the intensity variation that you had during the recording stage of that hologram, okay? And that gives you a clue. Later, we'll see that the efficiency roughly later I'll have you memorize this, but anyhow, this is for just an unslanted grading. So the efficiency is going to depend, this is the index modulation that you have in the film, and the film thickness, which is constant. And this is a sine squared function. So that efficiency can oscillate as a function of your delta ND, kind of your grading strength that you have in that hologram. And so if you have these variations, and again, delta N is proportional basically to the exposure that you have, all right? So if that exposure varies significantly, you can see a variation in that diffraction efficiency, which might be from a few percent to, you know, even 10 or 20% if you had really large intensity variations in that exposure. So that's what this is to get you to consider. And since you matched it at the center, you might guess that that's probably going to be the best efficiency, right? Because that's your one-to-one visibility is right there. And that's where I asked you to match the efficiency or match the exposure energy density or power density to get the exposure that you need for kind of this optimum index modulation, optimum efficiency. Okay. All right. Okay. So the next thing I want you to do here is, so now you've probed it and you kind of sampled the efficiency across the aperture. So the next thing I want you to do is, all right, illuminate the whole aperture, measure the diffraction efficiency with that condition, and you'll compare it to your kind of probed values across the aperture, only 5, but you know that'll give you a reasonable average. See if that average looks kind of similar to what you have for this total efficiency, all right? So do that. And also, then what I'd like you to do is to kind of tilt the hologram a little bit when you illuminate it with the full beam there, and see where you get the maximum efficiency. See if you can get, you want to do that also here with these individual exposures as well. Just tilt a little bit. You have to be a little careful because the beam's going to kind of, or the hologram's going to walk off a little bit. It's not going to be centered except at the center. So you have to be, can't tilt it a whole lot. You don't need to probably. But anyhow, see if, the settings for the exposure match very well with the reconstruction for maximum efficiency, is what I'd like you to see. And the other thing you could see is, excuse me, you can see is how nice a spot you're able to produce during that reconstruction. Excuse me. So what you should get is a nice point image, all right? Ideally, you'll get a nice point image. But if you had changes in the material, for instance, if, say, the average refractive index changed, or if you had to tilt this a little bit to get the maximum efficiency, you will start to see some aberration. We're going to talk about those shortly, probably next lecture. I don't think we'll get to it today, but very shortly we'll talk about some aberrations. And we'll see how sensitive they are, or how sensitive the hologram is to different changes, both spatially and spectrally, in the reconstruction process. So I want you to kind of get a little feel for that and see if you... Which do you want to see?
Well, you were gesturing to the paper as you were sliding it off.
Oh, this paper,
So,
or this paper?
top paper you were gesturing to, and it seemed like you were sliding it off.
Okay, I'll try to be more coordinated. So, at any rate, if any of you, know your aberration, so you have, spherical coma, astigmatism, and field curvature and distortion. So, if you tilt this, you'll find kind of a dominant aberration. So you can see, see the aberration pretty nicely. So, again, if you're not familiar with that, don't worry about it. But so let me tell you. So spherical, we kind of talked about. Spherical is just, this beam spreading out a bit here. So you may have, maybe like this focal shift will give you a larger spot there than what you think you might need. And then the other one that you have is coma. So coma kind of looks like a comet's tail here. So you have a lot of intensity here, and then you have a lot of spreading out there. All right, and so when you tilt this, you'll probably see coma, just in case I don't want to have those who haven't had aberration analysis be at a disadvantage. But, again, just kind of explore that a little bit. And you can expand that spot, use a camera and another lens to magnify it a little bit and just image it onto a camera to see it a little bit better if you can't, or just project it on a sheet of paper or something. So kind of get an idea what's happening in that image reconstruction. You should be able to get, again, if this focal length is long, your F number is large in this this lens system that you have, that's what you're going to record, and so you'll be less sensitive to aberrations in that large F number system, as we'll see when we do the aberration analysis. Okay, so that's pretty much the lab. Any questions on that? So I think it's loaded on the website. You should have it, and you'll be doing that Monday and Tuesday. Okay. Okay. All right. So back to our image analysis. So we were kind of developing a kind of a set of tools for image analysis. Of our holograms. And so we ended up with, last time we had our exact ray tracing relationships that we had. So we have our ray diffraction at the hologram. So this gives us the angle change. And so here we had this in a set of direction cosines, which makes it easier for doing actual calculations. So we have Li for the image direction cosine. So L is a cosine of alpha, M is a cosine of beta, and N cosine of gamma. And so again, we have our ray with unit direction, and so we have x, y. No, that's not right. I want z over there. Y and x. And so this, again, this is the projection along the x-axis with a alpha and so forth for the different. So again, y gives us, we have that beta, and z gives us the gamma. So we have the image direction cosine is LP minus Q times the reconstruction wavelength over the construction wavelength times LR minus LO. And so this is the reference beam during construction. This is the object beam, and that's the reconstruction beam designation for the point sources that are used during construction and reconstruction. Similarly, we have, for the relative to the y axis, we have Mi is MP minus Q, which is the diffraction order, lambda 2 over lambda 1, Mr minus Mo, and then Ni, using our direction cosine law, is just the square root of 1 minus Li squared minus Mi squared. Okay, and then we had, in addition to the, so we have this for the angle change, and then we had for the transfer relations, we have that xi on our evaluation plane is equal to Ri Li plus xh, where xh is the coordinate. I think I have nice figures somewhere. Is the coordinate on the hologram plane. Here we go. Why am I rewriting all this? So it's right here. So we have xi is Ri Li plus xh. So here we have a coordinate on the hologram plane, xh, yh, 0. A local grading vector, k, at that position. And similarly for L, or I'm sorry, for y, yi, for the image. So here we, again, transfer the xh, yh over to the distance zi away, which is our image evaluation plane. And we add to that the kind of the tangent of this distance that we have, Ri times Li. Okay, and Ri, again, is just, Ri is equal to xi minus xh squared plus yi minus yh squared plus zi squared, okay, to the 1/2. All right. Okay, so we have, these ray trace relationships, and that's great, but we'd like to get a little more feel for instance, where should we place where's our image plane, okay? So the basis for our image plane will be, the paraxial image location. And so we're now going to look at, the formation, or how can we come up with a set of relations to describe this paraxial position. And also we can find that we'll have, once we get that, we can kind of develop a set of other relationships for common things of interest like magnification, spectral bandwidth, and other things like that. All right, so as we were in the beginning, or at the end, I should say, of last lecture, we were kind of talking about how to go about doing this. And so here, if we have our hologram plane, and we have some aperture out here, and then we are going to have some distance over to an evaluation plane, distance z. And here we have our x and, I'm sorry, I'm using x and y. I normally use them differently, but for this I'll just use it this way. Bear with me. And here we have, x, say x1 and y1 coordinate system. And so here, if we have a point in the hologram plane and we want to know what the phase is out here at the evaluation or the image plane. So we have a point out here, P, of x, y, and z. And here we have a point S, x1, y1, and we'll set that equal to z equals 0. We can get the phase by taking the path length difference and multiplying it by 2 pi over lambda. So as I mentioned, though, we would get a very large number for that. So often it's useful to reference this phase to a position relative to the axis here. So we have 0, 0, z. So we'll call that O, all right? And so our phase that we'll take, it will be what we'll refer to as a referenced phase. Referenced in the sense that we'll take the phase as, again, 2 pi over lambda, assuming air here, times SP minus SO, or SPO, or whatever we want to call it at the origin. All right, so if we develop this now, write it out in terms of our coordinates that we have. So this phase then, phi, is now, again, 2 pi over lambda. And so we have our difference in distances. So we have this distance and that distance. We take the difference of those. And in terms of coordinates, we have x minus x1 squared plus y minus y1 squared plus z squared. That to the 1/2 minus this distance here, from here to the origin. So here we just have x1 squared plus y1 squared plus z squared again. That's to the 1/2. And so now we could factor out a z out of that. And so we have 2 pi over lambda times z. And writing it more suggestively, 1 plus x minus x1 squared plus y minus y1 squared over z squared, again, that's to the 1/2, minus 1 plus x1 squared plus y1 squared over z squared, that also to the 1/2. Okay? All right, so we haven't done anything there, but as you can see, it's suggestive in the sense that we want to get rid of this radical, so we can again use the binomial expansion. which works, gives us a set of terms to describe this series described by that quadratic. And this works provided b is less than 1. So again, so if we make a mild restriction there of saying that our distances laterally are less than the distance longitudinally, which is usually the case, we're in good shape to use that binomial expansion. And so now we have phi is, again, 2 pi over lambda z times 1 plus, just use the first two terms of this expansion, 1 plus a half x minus x1 squared plus y minus y1 squared divided by z squared. So we have that minus 1 plus 1/2 x1 squared plus y1 squared over z squared. Okay, so if we look at this, we see that these 1's cancel out. And what we're left with is that phi is equal to 2 pi over lambda z x squared minus 2x x1 plus y squared minus 2y y1 over, just expanding this out and combining now, over to z squared, or simply pi over lambda z, that is down there. Pi over lambda z times x squared plus y squared minus 2x x1 minus 2y y1. Okay, so again, what we've done is, by doing this sort of referenced phase, we've kind of simplified the phase relationship to a term which depends on these coordinates in the image plane and also the coordinates in the hologram plane. Okay. All right, so now when we form a hologram, we have to worry about several different sets of points. Okay, so we have the reference beam. All right, so this is our reference beam here. So this has coordinates xr, yr, and zr. Okay, and this we can say has so we have a field here that's a sub r. We have an amplitude a sub r times a phase, e to the minus j phi r. And then we have an object beam O with xo, yo, zo, and this has a field term a0, a sub 0 for the magnitude, e to the minus j phi 0, and then we have our reconstruction beam, which is p of, and that's xp, yp, zp, and it's similar, ap equals ap e to the minus j vp. All right. Okay, so that's our set of fields that we have, and so during the recording, what's going on? The field at the hologram is now going to be described by if these are points, these are point sources, okay? So these are the point sources used to form the hologram, all right? So again, so we have these point sources sitting out somewhere in one plane, and then we want to find out what happens when we illuminate that hologram, all right? So when we do that, we say that, all right, the field at the hologram now is, say, u sub r0, and on the hologram we're going to use the coordinates x, y. Yeah, I'm sorry, I thought something was a little screwed up. I should look at my notes. So this, let's say this is a source plane here, and this is the hologram plane. That's much better. So the source plane, again, has x1 and y1, where now x1 and y1 are going to correspond to either an xr, an xo, or xp. And on the hologram plane, we have kind of the general coordinates or variables x and y. So these are actually, these are fixed points, but these are variable points or variables. So, okay. All right. So here's our field. Yeah, this looks a whole lot better now. So here's our field u sub ro of xy, and so we construct, we illuminate it with these two fields, r and o. Right. So we're going to have ar exponential of minus j 2 pi over lambda 1 zr. Okay. Sorry if I'm using upper and lower case interchangeably. And lambda 1 is the construction wavelength that we have. All right. And so this is now using our result that we have up here. This is times x squared plus y squared minus 2xxr minus 2y yr. All right, so that's our reference field, and then we have the object field is similar, exponential of minus j 2 pi over lambda 1 again during construction, zo, x squared. Again, these are the variables in the hologram plane, x squared plus y squared minus 2x xo minus 2y yo. Okay, so this, as we've done many times now in the past, this is going to form the transmittance function right? So t now is going to, if we take this and do the square of that, uro squared, this is going to give something that's proportional to that intensity from that interfering field. So we have this interfering field on the hologram plane giving us the hologram eventually. And so now, so we have, let's say we have the hologram. So now what we're going to do is do a reconstruction. Right? So for the reconstruction, we're going to use this source point P here. So we use source point P for the reconstruction, and that's going to have a phase phi sub P, which is pi over lambda 2, right? So lambda 2 equals the reconstruction wavelength. Lambda 2 times distance zp times x squared plus y squared minus 2x xp minus 2y yp. All right, so that's the phase of our reconstruction beam. Okay. All right, so we're going to take so we take the field here, which has, so here's our reconstruction field, and then we're going to take that and multiply it by this, right, as we normally do. So we're going to take our yeah.
Is there supposed to be a 2 pi in the recording field? Because you have a 2 pi in the recording field, but not in the reconstruction.
Okay, thank you. This is not here. Sorry. Okay. Yeah, it should just follow what we derived up here. Yeah. Thank you. I sometimes just automatically write 2 pi. So. Okay. So again, so what we do is as normal, we're going to take AP and multiply it by our transmittance function, and that's going to give us our image field, right? So here, the image field that we end up with, U sub I, is going to be, again, so we have AP times e to the minus j phi p times AO squared plus AP times e to the minus j phi p times AR squared. And then we have the terms of real interest here, AP times e to the minus j phi p times AR star AO, and then AP e to the minus j phi p AR AO star. So we can call this, so we have these different terms. So here's U1, U2, U3, and U4. All right, so those are the 4 fields that are reconstructed during the illumination in the reconstruction phase. All right, so we have these 2 terms here, and so if we combine all of these terms, we could say that we have a U3, which is equal to the magnitude of U3 times e to the minus j phi 3, and we also have a U4 magnitude e to the minus j phi 4. Okay? All right, and so these are, again, so these are the 2 terms of interest. And so what do we have for those? Well, we have U3 equals AP AR star AO. Okay, all these are sort of complex. And so we have AP AR AO, and then exponential of minus j times phi p minus phi r. Oops, I didn't mean to put that there. Plus phi o. And then for U4, we have kind of the similar thing here. AP AR, this time AO star, and then AP AR AO exponential. The main thing here is this phase. So the phase on this is minus j times phi p plus phi r minus phi o. Okay. So we have these these phase terms, and so we have a composite phase for U3, right? If we wanted to write this, we can say we have a phase for this U3. So again, so U3 is, say, an A3 times e to the minus j phi 3 is what we're calling that. I'm going to put a little 1 there because this is the part of how phi 3 is derived, and it's directly coming from this composite of our standard hologram construction and reconstruction. Okay, so this now we can write as pi over lambda 2, and lambda 2 is our reconstruction wavelength, and then we have that times x squared plus y squared times 1 over zp plus mu over z0. Now mu, we have two wavelengths, right? So we have mu is the ratio of the two wavelengths, lambda 2, the reconstruction wavelength, over lambda 1, the construction wavelength, minus mu over zr. And then we have minus 2x times xp over zp plus mu x0 over z0 minus mu xr over zr. And then we have minus 2y yp over zp plus mu yo over zo minus mu yr over zr. Okay, so so that is just straightforward algebra from our hologram construction process. All right, and so again, that just represents these three terms where we have the phase given by this relationship for each one of those. Okay. All right. So what we're claiming here is that the hologram is going to form an image. All right. So what do we mean when we say that something forms an image? All right. Well, if we have what we mean by an image is that if we have an object point, we have an image point. So there is some correspondence between 2 points. So we're either going to have, for an image, we either have to have a wave converging to that point or diverging away from that point. Okay? Just, kind of image, what we would call that, image definition, right? So we either have a converging or diverging point, corresponding to an object point. That's what we mean by an image. All right. So now what we could say is that we also can have so this field has another sort of significance or another meaning. All right. So now we can say we have a phi3. We'll give it a different superscript to kind of separate that. But this particular phase corresponds to this point where light is either converging or diverging to. Okay? And so this is equal to simply this relationship up here again. But now we have a different point corresponding to that x1 and y1. And we'll call that x3 and y3. So we have pi over lambda 2 z3. This times x squared plus y squared. Again, these are points. We're taking a phase from a point in the hologram to the image point. Okay? So we have x squared plus y squared minus 2x x3 minus 2y y3. Okay? And again, so what that corresponds to is we have some point here, x and y, and when we illuminated this with our UP, we are getting, again, say convergence to a point out here, and we're going to call that point x3, y3. Okay? So what I'm claiming is that these two have got to be equal to one another. All right? And that setting those two phases equal to each other are going to give us the paraxial relationships that we've been seeking. Okay, so if we equate those, right? So here we have we can equate the different coefficients of, say, x squared, y squared, x, and y. And so what we want to eliminate the hologram coordinates out of this relationship. Okay, so for instance, if we now look at just the x squared coordinates, so we have x squared for this one x squared over lambda 2 z3. This is going to be, this part is equal to that. So this is going to be equal to 1 over lambda 1 times 1 over, lambda 2, zp plus mu over zo minus mu over zr times x squared, right? So then we can drop that, and we now have a relationship, as you can from that, that's going to give us, say, z3, the position of that paraxial image point. Okay, and similarly we have for the x parts, so we have a minus 2x x3 times pi over lambda 2 z3 from this part, and we set that equal to that part. All right, so that's again minus 2 pi x over lambda 2 times xp zp plus mu x0 over z0 minus mu xr over zr. All right, and we now eliminated the variable x that was in the hologram plane. Okay, so we now have it. All right, we do the same thing for y, so I won't need to do that. And so we end up now with a set of relationships for this phase matching, which again tells us where the image should be from this reconstruction. Remember, we assumed again that we're going to get points, or the wave is either converging or diverging to a point out in space at x3, y3, z3. So we have x3 solving this for all the algebra. Again, there is some algebra here, but anyhow, xp zo zr plus mu. Again, mu is the lambda 2 over lambda 1, so we can have different wavelengths between the construction and reconstruction phase. So here, mu x0 zp zr minus mu xr zp zo over zo zr plus mu zp zr minus mu zp zo. So we have x3 that's only in terms of the coordinates of the source points that were used for the construction, O and R, and the reconstruction, P, and the two wavelengths, lambda 1 during construction, lambda 2 during reconstruction. Similarly, we have y3, looks kind of like the same here, except we substitute y for x, so yp zo zr plus mu yo zp zr minus mu yr zp zo. So you see here it just kind of rotates. You have a p, o, and r in each of these to keep things straight. And then zo zr, same denominator, plus mu zp zr minus mu zp zo. And then our z3 is zp zo zr over that same denominator, zo zr plus mu zp zr minus mu zp zo. Okay. Okay. Now, an important point here is, so we formed the hologram and reconstructed it again with this field that it just has an arbitrary amplitude and phase. So let's just say we have a unit amplitude, but it has an arbitrary phase. So we haven't really said yet whether that is the original reference field or the conjugate. It could be either, right? The way we determine that, or the way we set that, is by the coordinates of the relative coordinates between R and P. The point source R is our reference point source, and the point source P is the reconstruction point source. So we could change it. We could use the conjugate, we can use the original wave, and that's going to show up in a different image quality for these two different terms. But the important thing to remember is that we are always going to get both of these, okay, according to this formulation that we just have gone through. It's just the basic hologram formulation, but we're always going to get these two. The quality of the reconstruction is going to depend upon the type of point source we use for the reconstruction, the location and wavelength of that reconstruction point source. So we are going to have these two waves, and so we should kind of, and I like to designate them, one as the primary and the secondary. Whoops, writing over. Okay, so this is very similar, when we talked about the inline hologram, the Gabor hologram, where we had all of these overlapping waves and so forth. So we're going to end up with the same kind of thing here. We're going to have, provided we have some efficiency in that secondary wave or the primary wave if we use the conjugate. But they're both going to, the point I'm trying to make is they're both going to be there unless something really suppresses them. But one is going to have a better quality than the other depending upon how we reconstruct it, okay? Which is kind of what we've said all along, but this kind of shows up in the image analysis, in the paraxial image relationships, okay? So we have a set of relationships for, this is again corresponding to the primary, and also for the secondary, we're going to have a set of points x4, y4, and z4, which are going to look pretty similar, except the signs are going to be reversed in the relationships. So I'll just write out the x1 here. So here we have, say, xp, zo, zr, minus mu xo, zp, zr, plus mu xr, zp, zo, divided by zo, zr, minus mu zp, zr, plus mu zp, zo. So as you can see here, we have a reversal of the signs between the primary and secondary image. Now, it doesn't really mean that this one is a virtual image, this one is a real image. That's all going to be a function of what that reconstruction beam is, what the P source is, okay, and where the coordinates are for that. Okay, so we will continue on this next week, and also please come to your lab assignments on Monday and Tuesday. Okay, have a good weekend.